Hello, I'm Dr. David Kordwitz and welcome to programming. Today we're going to talk about the ideas of algorithm design and flowcharting. These two ideas go hand in hand as a flowchart is a graphical representation of an algorithm. So let's go and take a look at how these work together and how you can come up with your own algorithm to solve problems even beyond what you think you're capable of. So let's begin. Let's take a look at someone's typical morning. They have a bunch of tasks which they must complete. Taking a shower, driving to school, getting dressed, the alarm goes off at some point, waking up. So if we look at these are in no particular order. So we need to somehow organize these into a series of steps that will help us get through our morning. So let's take a look at this, and we're going to come up with a list of steps, a list of processes. So the first step probably is that the alarm's going to go off. Now, this may not be true for 100% of people. You may wake up before your alarm goes off or whatnot, but for this purposes, the alarm is going to go off, and as a response to that, you're going to wake up. Once you're awake, the next step is probably going to be taking a shower. If you get dressed before taking a shower, well, that doesn't make any sense. So let's go ahead and take a shower, and then after that shower, we're going to get dressed. And then the last step is driving to school. So this right here is an algorithm for waking up in the morning. Now we can represent this graphically using a flowchart like this. Now if you notice, we start at the beginning and end at the end, and we sort of go through this process step by step. Now, it's important to note that this process is what we call a linear process. In other words, we're going through step by step through our algorithm, and there's no reason to deviate from any of the given steps as you move along. Now, not all problems are like this, so let's take a look at a different morning. So in this morning, we have to take a shower, drive to school, get dressed, alarm goes off, wake up, grab an umbrella. Well, if we look at this process, the alarm's going to go off, we're going to wake up and take a shower, we're then going to get dressed, and now we have to ask ourselves, is it going to rain today? It doesn't make any sense to grab an umbrella if it's not going to rain, because then you're going to be stuck carrying it around all day. So we need to ask the question, is it going to rain? If yes, grab the umbrella. If not, don't grab the umbrella. And then the last step will be drive to school. So it doesn't matter whether you take the umbrella or not. The last step is the same, and all the preceding steps are the same. So when we do a flowchart, it's going to look a little different. It's going to look like this. So after we get dressed, we have one of these triangular nodes or diamond-shaped nodes here that's going to say, is it going to rain? If yes, grab umbrella. If no, drive to school. And you can see by the direction of this arrow that after you grab the umbrella, you still go back to driving to school. So you can see that an algorithm can very quickly be put together into this flowchart type setting, and you can follow the steps step by step through your flowchart. Now, flowcharts have been used for years and years and years in the computer science and process engineering world. Flowcharts consist of a set of standardized symbols. We have 4 that we're going to discuss here, but there are many, many, many other ones that you can use if you need to. We always start and end with this sort of oval-shaped, slot-shaped logo, and you literally put the word start or the word end inside of it. And that tells you where the algorithm starts and the algorithm ends. Alternatively, if you have to continue on to a different page, typically the symbol for that looks something like home plate in baseball. The next one that we have here is a process. A process is a step along the way. So what you want to do is granularize the steps as you go through your algorithm to basically be small enough that you can do them in a process, but not so large that you basically make one process box and say, solve the problem. You want this to give you the steps to solve your problem that you want, so that when you're ready to write a program with it, you know what the steps are, and literally each of these boxes should translate to one or a few lines of code. Additionally, this diamond shape here is what we call a decision. In a decision, you have to answer a yes or no question, or in some cases a 3-option question, but I wouldn't go much beyond that just because things will get messy. But you can do an if it equals this, if whatever. This is where you can ask those questions that either have a yes or no and very few answers. The last one is what we call an input-output box, and this one is one that there's a few different diagrams for depending on whose flowchart you're looking at. Some of them, the parallelogram goes to the right for output and to the left for input. There's a few different conventions on this, but all of them generally look this way. And that's basically you're either getting something from the person running your program or you're giving something to the person who's running your program. So basically printing to the screen or getting data. Additionally, this can be from files or from other things like that, but that's for a later date. Okay, so let's take a look at what pseudocode is, and then we can look a little more into the details of algorithm development. Pseudocode is sort of a non-standard method in that there is not a single pseudocode layout that everybody has agreed upon. There are dozens, if not hundreds, of different pseudocode layouts, but they all try to accomplish the same thing. They try to basically give you the algorithm how it would need to be written in code, as opposed to sort of writing them in code. And part of this is because you can do this independently of the programming language. So this is more of a for your benefit type thing as opposed to actually producing the final code. So let's take a look. This flowchart here gives you the ability to compute the roots of a quadratic equation. So what we do is we start and we ask the user, what is the equation? We then ask ourselves, is this equation actually a quadratic equation? If it is, we can continue forward. If it's not, we're going to display an error message and say, please enter a quadratic equation, and go back to the top to continue with the algorithm, and we'll keep going in this loop until they give us a valid equation. Once we have the equation and we know it's valid, we're going to go ahead and use the quadratic formula to solve our roots, and then we'll go ahead and display the roots to the user, and we end our program. So what happens when we want to do this in pseudocode? Okay, so let's start here. So we have our algorithm in a flowchart, and we want to convert to pseudocode. So the first question we have to ask ourselves is, what are our inputs? So what do we need from the user? And what we need from the user in this case is the equation. So our inputs are the equation. We then have to ask ourselves, what are the outputs? Well, the thing we're hoping to get out here are the roots of this equation, or as I'm going to call them, R1 and R2, because as we know, quadratic equations have two roots. So the next thing is, what are our variables? So what are things that we need to hang on to and we need to keep stored? Well, we need to store the equation that's provided to us, R1 and R2, because those are the things we're going to actually use throughout solving our math. So what are our steps of this algorithm? So the first step is, let's input the equation. So I'm saying input equation. We're then going to say, if the equation is quadratic, then root 1, R1 is equal to this, the quadratic formula with the plus, and R2 is equal to the quadratic formula with a minus. So once you get this, what are we doing? Well, we're going to display it. So we display R1 and R2, and that's going to end what happens if we actually give a quadratic equation. Now, otherwise, or else, if we don't come out that the equation is quadratic, we're going to follow these instructions. And basically that instruction is start again from the beginning. That makes kind of a lot of sense because we're going to go back to the top and input the equation again. This then ends our pseudocode. So now, if you're clever about this, and once we get a little more into programming languages, you will be able to convert this pseudocode into a working program without much effort. This is increasingly important as you sort of go through setting things up, because now you can take pseudocode that's written for one programming language and use it in another. So that's really critical. Okay, so now that we understand our tools, we now need to look at algorithm planning. So one example of an algorithm, it's a computer program or a process of steps. So for the purposes of our experiments here and our discussion, we're going to use a chocolate cake as our A chocolate cake is what we're trying to accomplish with our program. So basically, it's always best to sort of figure out these algorithms and figure out how you're going to bake the cake, for example, before you begin to actually bake the cake. Because if you start writing code or baking a cake for that matter without any instructions, you're going to mess something up and it's going to get you frustrated, and you're going to keep going and going until things basically fall apart. So remember to figure your algorithms out before you actually put any code into your integrated development environment or IDE. It's important to also realize that when you're doing programming, you are doing problem solving. It's not about the actual code itself, but rather figuring out how to solve the problem and then making the code work for you. Now, a lot of people get tied up in the little details of the code, but that's not really all that important. What's important is getting through that algorithm and understanding how to solve the problem so that when you do hit an error when you're coding, you know exactly what is going wrong, or at least you know how to backtrack and figure out what's going wrong. So how do we develop an algorithm? And it's a cycle. It's part of the software development life cycle. So you may see this in some compilers and things listed as the SDL. Basically, the idea is it's a series of steps that we need to use when developing an algorithm. The first thing we need to do is figure out what the problem requirements are. So like, what do we need from the user? What do we need to sample? What do we need to do? The next thing you're going to do is analyze the problem. So basically, what do I need in? What do I need out? What are the possible hang-ups? What could go wrong? Those sort of things. You then go ahead and design your algorithm to solve the problem. So basically, you're going to go through and you're going to find what tools you need to actually solve the problem that you've just analyzed. You then go ahead and implement the algorithm in some form of programming language, whether it's C or Java or Python or MATLAB or whatever. You're going to go ahead and implement it as a program that's runnable. You're then going to test and validate the program. So this means going into an alpha test or a beta test where you're going to give your software to some people to try out, but at the same time be monitoring to look for errors and problems. Now, it's important to note that your code will never be perfect. It doesn't matter how simple it is. There's always a bug somewhere in the code. Now, that said, it may be a bug you never run into or a bug that never affects you in any way, but just know that there's always ways you can make your code better. But that said, usually you want to get it so that it works and it gets out there fast enough, and then you worry about maintaining and updating the program after its initial release. So when you develop software, you want to go through this cycle, and the maintenance of this program is typically going to lead eventually to the next version of it or an updated version of the code. So let's look at these steps and break them down. So the first step is our analysis. So when we're doing our analysis, we need to determine what our inputs and outputs are. So what can you ask for? What are you going to use? So, and then what are you going to supply? So basically, what is the user giving you? What are you giving the user? Those sort of things. You also need to look at requirements. So for example, if you need a program to run on a Android phone, you really don't necessarily want to write it in Swift, which is the iOS language. You want to write it in the language that's appropriate for the Android phone, which is Kotlin. So one of your requirements is going to have to be runs on an Android phone. Now, sometimes this doesn't matter, but typically you need to look at what are the requirements for the software as well as what are the constraints for the software. So what do you need it to be able to do, as well as what do you really have, what walls are you going to hit? So typically constraints end up being things like time, money, operating environment, things like, okay, well, if I'm going to write something for Windows, I'm going to write it so that it runs in Windows 10, but I don't really care about Windows 7. So, that's sort of the constraint, and the requirement would be runs on Windows 10. So when we do things like this, we could say, let's say we want to calculate the value of X and Y. Our inputs are going to be X and Y, and our outputs are going to be X plus Y. Okay, so how do we design an algorithm from here? Well, the first thing we need to do is break the problem into smaller chunks, into smaller subproblems. These subproblems, typically you know your solution to. So in other words, you know how to add numbers, you know how to divide numbers, but if you need to add and divide at the same time, you may just break that down into adding and dividing, depending on how you want to do it. You're then going to go ahead and write a flowchart or a pseudocode or something to basically map out your algorithm. The best thing you can do at this point is to test it on paper. In other words, go ahead and walk through, write numbers on the paper that show what the variables should be and what they solve to. This will help you catching bugs in your thought process, which will help you later when you develop your code into a real program. So that's what the next step is. The next step is converting your pseudocode into some real code. And you basically should look at your pseudocode and be able to convert each step and each process and each inquiry into single lines of code, which can then be translated and compiled for your computer. Another important one that we are not ready to completely go over are what we call variables. Now, when I talk about variables, I like to use a cardboard box as an example. And so what it is we put a name on the cardboard box, and that's what we're going to call it. And basically, we can take our data and throw it in the cardboard box. And so when we think about it, you want to name your variables. So we're going to talk about how to do this in a future lecture, but you want to name your variables with something that makes sense. Don't name all your variables X, 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 Y, Z, something like that. Actually, give it a name that, if you look at this in 3 months, you still know what the variable is. There's very few restrictions. In some languages, they don't allow special characters. I know in C, the only thing they allow is underscores. You can never start a variable name with a number. It doesn't like that. But these are constraints that are individual for the language you're working in. But that said, you should always name your variables in a way that will make sense to yourself. So let's take a look at our cake again. So if we start with our chocolate cake, we see that we need 4 ounces of chocolate, 1 cup of butter, 2 cups of sugar, 3 eggs, 1 teaspoon vanilla, and 1 cup flour. We're going to melt together the chocolate and butter, stir the sugar into melted chocolate, stir in eggs and vanilla, mix in flour, spread it on a greased pan, and bake at 350 for 40 minutes or until an inserted fork comes out clean. Cool the pan before eating. Obviously, if you don't cool the pan before eating, you're going to burn yourself, and it will not be good eats. Okay, so let's look at what we need. So the first thing is that we want to find out what our inputs and outputs are. Well, our inputs here are going to be the chocolate, the butter, the sugar, the eggs, the vanilla, and the flour. Our output from this is going to be a delicious chocolate cake. Okay, that makes some sense. So let's take a look at what our variables are. So variables are what we put things into, right? So in this case, we could say that it's the mixing bowl that you're mixing everything in. That's going to be your storage for everything as you combine it together. So let's take these instructions and convert them to a flowchart. So we're going to start, and then we're going to mix our ingredients, spread it in the pan, bake at 350. If you insert a fork, is it coming out clean? If it's not, continue to bake. If it is, remove your cake from the oven. Then you're going to let it cool. And that is the end of your algorithm. So you can see we have a bunch of steps. Now, that said, this mix ingredients isn't very specific, but you could break this down further to the individual steps of how to mix them together. So let's take a look at how we would pseudocode this. So this is an example of some pseudocode for this algorithm. Basically, we have some variables that we're going to say is chocolate, butter, sugar, eggs, vanilla, flour, and mix. We're going to say that our mix is going to be equal to the melted 4 ounces of chocolate and 1 ounce of butter and 1 cup of butter. We're then going to mix. We're then going to say that the mix is if we stir together the mix that we had before plus 2 sugar, so 2 cups of sugar. Then the mix is going to equal the mix we were stirring before plus 3 eggs and your teaspoon of vanilla. Then our mix is going to be our mix plus flour. We're then going to spread that mix out, and we're going to say while this fork is not clean. So basically, if you stab the fork and it's not clean, you're going to continue to bake. When it's done, you're going to take it out, cool it, and be ready to eat. So this is the basics of how you develop an algorithm for when you're programming and solving tasks. So I hope this has been informative, and thank you for your time today, and I'll see you next time.